Okay, so for simple harmonic motion, the acceleration is proportional to the displacement, and it's acting in the opposite direction as well, hence this negative sign. So acceleration proportional to displacement. Notation, the second derivative with respect to t of x, you can write that as x with two little dots on top, and similarly dx dt is x with just a single dot on top. I don't tend to use that shorthand. You're really welcome to use it, and I think they have used it in your online textbooks a little bit, so feel free to use if you want to. So we've got a particle moving along a straight line at time t as displacement x from a fixed point 0 is such that the acceleration is equal to minus 4x, and we've got some boundary conditions. So when t is 0, x is 1 and v is equal to 4. And we want to find an expression for the displacement of the particle after t seconds. So this particle is kind of moving that way, slowing down to 0, coming back, moving that way, slowing to 0, coming back. So it's moving backwards and forwards. So yeah, it could be attached to a spring. That would give you simple harmonic motion. So it's really an integration question. So we have that, I was going to go for blue, sorry. So we know that d2x dt squared plus 4x is 0. This is a nice easy one to solve. So the auxiliary equation is m squared. There's no dx dt term, so plus 4 equals 0. And all the simple harmonic motion equations are going to come out like this, because this is a very fixed form that you're dealing with. There's the auxiliary equation, and so m is equal to plus or minus 2i. I've square rooted this 4 here, so we're actually looking at plus or minus omega I there, if you wanted a general form, but I'm not going to focus on that too much, to be honest. And so we know that x is equal to a cos 2t plus b sine 2t from the work we did before. And I think I need a new board. We know that when t equals 0, x is equal to 1. Just write it out again. So t equals 0, x equals 1. So this gives 1 is equal to a times 1, so plus 0. So a is equal to 1. My cat's running around in here. And we also know that the velocity is 4 when t is equal to 0. If you ever need to get to the velocity, you can differentiate the displacement. So differentiating to get to the velocity with respect to t. So, sorry, my cat's really making me laugh. So I get minus 2a, but a is 1. So minus 2 cos 2t plus, oops, sorry, that's meant to be a sine. Minus 2 sine 2t even, so I'm differentiating this, plus 2b cos 2t. And when t equals 0, v is equal to 4. So 4 is equal to 2b, and so b is equal to 2. Substituting back into here, we've got x is equal to cos of 2t plus 2 sine 2t. And then the second part of this equation is to determine the maximum displacement, and then this whole equation will start making a bit of sense. So determine the max displacement of the particle from O, but I'm not going to write that down. So we're here. So we need to put this into r sine theta plus alpha form, and then you can work out things like the period and the displacement. So I need a 2t in my form. So I'm looking at doing r sine of 2t. This is a plus here, so it's going to be plus alpha. If that was a minus, it would go to, no, the minus would need to be there. But just go into sine 2t plus alpha form for these. And then that's equal to 2 sine 2t plus cos 2t. And then, so I was just trying to think we could go into a different form. I would stick with this if you can, but it's possible it might have to go into a cos form, I think. Or can you always do sine? Yeah, you may have to go into a cos form, but I think most of them do tend to go into sine, to be honest. So from here, if I expand this, I've got r sine 2t cos alpha plus r cos 2t sine alpha. So this is all maths stuff that you did in trigonometry, and that's equal to 2 sine 2t plus cos 2t. Equating coefficients, r cos alpha is equal to 2. And r sine alpha is equal to 1. And then if you draw your right angle triangle with alpha in, sine is opposite over hypotenuse, cos is adjacent over hypotenuse. And then you can use Pythagoras to get to r. So r is equal to the square root of 2 squared plus 1 squared, which is root 5. And if I divide these two, then tan alpha is a half. And stick to working on radians for these, especially if you're differentiating and stuff. So alpha is 0.464 radians. Radians, let's write that in just to make it clear. And so you can actually rewrite this as root 5 sine of 2t plus 0.464. So if you think about your transformations, the sine curve has been moved left by 0.464. Then it's been stretched by scale factor of a half. And then it's been stretched in the y-axis by root 5. I've put a graph of this in your lesson folder, which I graphed up on GeoGebra for you, and I've basically graphed the first 2 pi radians. In terms of the period is going to be pi of this, because you're going to have 2 cycles in 360 degrees, or 2 pi radians. And the maximum displacement, so sine is going between 1 and minus 1, so the maximum displacement is equal to the square root of the square root of 5 is getting a bit late. You should be able to work out the period from here. So suppose you had x is equal to 3 sine of 5t plus 0.3, for instance, then your stretch is here, so it'd be stretched by scale factor of a fifth, and so the period of this one is going to equal to 2 pi over 5. If you want to sort of memorise this in terms of your simple harmonic motion, you can convince yourself this will always be true. The period is equal to 2 pi over omega, because to get to this 2, we square rooted 4 here. That makes sense. So you could work with it like that if you want to. But they basically give you sine curves. So that's how you get your sort of oscillating curve. I've run out of things to say. Have a go at a few and get back to me if there's anything confusing. Thank you.